Good afternoon, everyone. Today, the Atom Seminar has the great pleasure of welcoming Professor Christelle Miqueu. Professor Miqueu completed her master's degree at Université de Pau Pays Adour and earned her PhD at the same university. She is currently an associate professor of the Laboratory of Complex Fluids and their Reserves at UPPA. Her research combines theoretical concepts with experimental data. Professor Miqueu has a strong background in modeling the thermodynamic properties of complex fluids, confined and nanoporous materials, and phase properties of organic and hydrate clarifieds. She also specializes in the characterization of nanoporous materials. In addition, Professor Miqueu has specific research interests in statistical mechanics and extensive expertise in density function theory. So once again, welcome, Professor Miqueu. Thank you so much for accepting our invitation. It is a pleasure to have you here with us. Please feel free to start your presentation.
The idea of the topic today is, of course, so as you said, one of the things I like to do is density functional theory, but as it's a very large topic, the idea is to focus on the characterization of nanoporous material, topic also of my research. And what I want to talk about is make the link between the DFT and the characterization of nanoporous material and see how this latter can evolve thanks to the last development that were made in DFT in the last years. So I will just show you the outline of the presentation. As I don't know, maybe most of you don't have the same background, so I will begin with the introduction on what is how nanoporous material are characterized thanks to gas absorption, to understand how DFT can be used in this characterization. Then I will say a few words about density functional theory, kind of general introduction. Okay, I take the laser. I will show you how it is already applied for the characterization of the nanopores and the latest developments that were introduced in the softwares of the porous imagers. And I will end with the recent DFT development and maybe begin to ask questions and begin discussion on how it will be, how it could impact the characterization of this nanoporous material. So first, let's say a few words about how gas absorption is used for the characterization of nanoporous solids. So when I speak about nanoporous solids, is that this gas porosimetry, so absorption of gases, is used for the characterization of the smallest pore, let's say below 30 nanometers, but for the one for which interfacial properties have the biggest impact. So how is it done in practice? The idea is that finally you want to analyze a network of cavities which are very small, most of the time disordered, and something that you cannot have a view on it, direct view on it. So the idea is to use an indirect method, and it's like if you want to analyze, let's say, an underground network of cavity, what will you do is that you will send, for instance, a diver, let's say, or a drone, to go inside the cavity, travel inside, let's say, and from that, you will have to have a kind of map of this network of cavity. And so it's what is done. So what is used most of the time in the commercial instruments is a manometry technique. Manometry technique, for people that do not know, is that if you want to know the quantity absorbed of gas inside a material, so I don't know why you do that, what you will have to measure is the drop of pressure that you will have before you put the gas in contact with the material, and so you do that with manometry. So you have a kind of reference cell cell with the sample itself, and then you send some dose of gases of a sample which is already empty, and you monitor the increase of pressure to deduce the quantity adsorbed at a given temperature, which is fixed, and by increasing the pressure. So to do so, from gas adsorption, you do it at very low temperature. So because you want to work also at very low pressure, and you need high pressure, high precision transducer to monitor the pressure and then measure the adsorption quantities. The probe molecules that are traditionally used, the most, let's say, traditional one is nitrogen, because it's you can work at atmospheric pressure, from very, very low pressure to atmospheric pressure at the liquid temperature of bulk nitrogen, 77 Kelvin. But then it was shown that due to interaction that nitrogen can have with the surface, it's better to use most inert, let's say, molecule, argon. It was what was preconized by UPAC a few years ago. Now you begin to have more and more CO2 adsorption at 0 degrees Celsius. The idea is to go to investigate smaller spores, because the kinetic diameters of CO2 is smaller than the one of these two molecules, and begins to appear also other probe, even if the routine is not very clear for the moment. And so the idea is that you measure what's called an adsorption isotherm. So you measure the quantity of the gas that is adsorbed as a function of pressure at a fixed temperature. And so you understand directly that it's a very, let's say, it's a macroscopic measure. And what you want to do from this macroscopic measure is to obtain finally the textural properties of the material at the microscale. It can be surface area, pore size distribution, porous volume, and so on. So what you have to keep in mind first is that it's really an indirect method, and an ambitious method also, I think. And to do so, there are several ways, but the way is the most, let's say, efficient way now is to use some thermodynamic modeling to go from this information at the macro scale to this one at the micro scale, meaning that you need to do an interpretation of this experimental isotherm of the global sample. And with that, you're going to use thermodynamic theory to obtain the cumulative volume as a function of pressure. And if you derive this cumulative volume, you will obtain what we call the pore size distribution, that gives you the number of pores of a given size inside the material. I just cited UPAC, and from the last UPAC, 2015, what was said is that, okay, the best way to do so is to use this integral adsorption equation, which makes the link between the global adsorption inside the material with the adsorption inside each individual pore. And you have finally the global contribution, which is a kind of continuous weighted sum of the contribution of each individual pore. So here also what is very important is the assumption that you use when doing so. First, the external area of the material is neglected, but it's a very small assumption because the internal surface area is very big in comparison. But the second hypothesis is very important. You make the assumption that the total adsorption, let's say, for instance, in this part of the network, will be just the sum of the adsorption inside individual pores. So you completely neglect the connectivity by doing so. And it's something that I will discuss at the end. So the process is like this. You measure your experimental global isotherm. You need to have this information from theoretical models, and that's where DFT comes. And you, from DFT, you are able to compute what is called a kernel, meaning the families of isotherm of all the individual pores. And you need to solve this equation to find this pore-size distribution. I won't go into the details of how it is solved, but it's thing that written here. It's with non-negative least square method, and of course with regularization, because it's an ill-posed problem, and you don't have enough information in that to have directly the let's say the good solution. So this is the main idea, and so now we are going to see how do we obtain this kind of kernel, and this is done with density functional theory. So I will tell a few words about that, being maybe quite quick at the beginning, just to be sure, because I don't know the audience, but most of the times when people think about density functional theory, they think about the quantum version of it, because the initial version presented by Kohn, Onenberg, and Sham, which finally deals with the electronic density of an atoms. This is for the most famous version of DFT. It's not the one we are dealing with, but this is the origin. And just in a very rapid way, what did they say about that is that they have demonstrated that it's if you want to study quantum systems, it's possible to study it without, let's say, considering electrons individually. You can do in a most efficient way, at least computationally, by knowing and working on the electronic density. And they have demonstrated that the knowledge of this electronic density is sufficient to obtain the energy of the system, and finally to obtain the other properties, all the properties of the system itself. And what they have shown is that the intrinsic part of the free energy is a unique functional of this electron density. Functional meaning a function of a function, because this density is a function of space. And the equilibrium state is for the electronic density that minimizes this free energy functional. And finally, let's say 10 to 20 years later, in the late 90s, Bob Evans have shown that these results are also true for classical systems, not quantum system, but classical one, and then began the development of DFT for inhomogeneous classic fluids. The main ideas are the same. Now you consider the free energy of, I said it here, an inhomogeneous fluid, but it can be a system, thermodynamic system, and you can find it as a unique functional of this time the molecular density. And the minimization of this free energy will give you the equilibrium density, meaning the microstructure of the fluid. Why this is an interesting technique? Essentially because the computational cost is very low in comparison with molecular simulation. Else, this is the main advantage, because else it's more difficult to construct, and I will show you that later, to construct especially the expression of this free energy. But once you have this free energy among a given set of hypotheses, you can obtain the equilibrium densities, and then you can compute all the relevant thermodynamic properties of the system, density profiles, interface tension, solvatation force, and so on. To do so, I will just focus on adsorption studies. So for adsorption, you will use DFT in the grand canonical ensemble, because finally your adsorb fluid is at a given temperature in a given pores of, let's say, for the moment, fixed volume, and in equilibrium with the reservoir. So the good thermodynamic properties is for sure the grand thermodynamic potential, which is, all of you knows for sure the expression in the bulk phases. And in DFT, you have the equivalent for the inhomogeneous phase, in which now this grand potential is a function of the density, which is function of the location in space. So the terms of functional, you still have the Helmholtz free energy of the functional of the density itself. And now you have this thermodynamic contribution. Finally what causes the inhomogeneity is the this potential, in which you have the bulk chemical potential and then the excess of density coming from the external potential acting on the fluid. For instance, in what we are going to see, the external potential will be the interaction potential exerted by the solid on the fluid itself. What you can do now is, traditionally, you split the free energy into two contributions, the kinetic one, the ideal one, and the excess contribution due to the molecular interaction between the molecules. From statistical mechanics, the ideal contribution is known exactly. This is the expression. So nothing more to do about that. Which is more difficult is the excess contribution that accounts for the molecular interaction, because there is no exact expression for that. So you have to build it, which is also a challenge, because you can to build it for and adapt it for any system you want. Here also you can split the contribution in a repulsive part, attractive part, hydrogen bonding, coulombic interaction, and so on. Once you have all these elements, you minimize the ground potential and you obtain the density profile. People working on DFT most of the time present the equation like this by combining the minimization of the ground potential with this expression of ideal part that allows you to show that, okay, the density profiles here is a kind of perturbation of the bulk potential with three terms. And finally, these three terms are the three inputs you need to have to apply your theory. The first one is the excess bulk chemical potential. This later can be obtained together with the bulk density from any bulk equation of states. Here you have the intrinsic inhomogeneous chemical potential. And then here you have the external potential, and you have to define all these three parts. Rapidly for the bulk properties, when you adjust for focus for the moment, when you're dealing with gas porosimetry, I've shown you that the fluids that you are using are rather simple. But by rather simple, I will say argon and nitrogen. It becomes a bit more tricky for CO2, but you're using rather simple fluids that can be most of the time modeled by Lennard-Jones fluid. You are at very low pressure, so it's not really a difficult task to obtain this term, and they are done with classical interaction potential in the midfield approximation. This is what is done classically in the theories that are used in the gas porosimeter software. For the excess part, it is split, as I said, in two ways. For the attractive part, it is taken as a perturbative treatment of spherical particles. And the Vertem term that you have for the attractive term is this one. And the difficult part is having there the per distribution function. But in gas porosimetry, here also due to the thermodynamic condition, it is the simplest way to take it into account is to use the mean field approximation, meaning no correlation between the molecule, and it's what is classically done all the time. And so you obtain this more simple expression for the attractive part of the free energy. And the last term is the hard sphere contribution. So the short-range repulsive interaction. What you have to do absolutely is to, you cannot use a local density functional theory, so a local approach just by taking into account just the density at one point, which is often done for, let's say, fluid interfaces, but that really does not work when you have adsorption inside micropore because the density gradients are too big. So you deal with what are called the non-local versions of DFT. So you take into account the vicinity of a molecule for this short-range interaction. To do so, you have two ways to do, and the two ways are used by the gas porosimeter software, let's say. The most often route that is used is the coarse graining introduced by Tarazona. in which you take into account weighted density by considering an average density inside a given volume around the molecule. You can do it with this Heaviside function here, and which is most often used now for people dealing with DFT at high pressure, and it begins to come also in the porosimeters, is to use fundamental measure theory, which is, I won't go into detail about this, but you will use also weighted density, but now you would use the measure, let's say, of the contribution. So not just a volumic contribution, but there's also surfacic or contact contribution. What you have to keep in mind is that you have a kind of weight that allows finally to take all this contribution, and you don't have a unique weighted density approximation. And finally, the external potential that gives the interaction between the fluid and the solid. Most of the time, and what is used is integrated potential, because to have a continuous expression, such as for the other term, the most classical one is to the integration of the Lennard-Jones interaction by differentiating the first layer with the other one, and it's an approximation which is called the Steele potential. So you consider an integrated potential on the first layer and then a kind of bulk solid, and you obtain what we call also the tensor 3 Steele potential. And then you add the contribution of X4. I will also give more details about that in the next section. So these are the inputs that are traditionally used most of the time. When you have selected this input, you can compute the density profiles in each pore, the integration of the density profile. So these density profiles, keep in mind that for sure they depend on the pore shape and the pore size. You integrate them, you have the total atom quantity, and by changing the pressure, you can build like that the adsorption isotherm. And so with this, you obtain what you were expecting for obtaining the pore size distribution, is what I called previously what is called the kernel, meaning the family of isotherms. Here it's an example of water in the graphitic slit pore, but you have for each pore size, you fix the temperature, you evolve the pressure, and you have the contribution of each individual pore. So you choose this kernel for a given fluid, at a given temperature, in a given shape of pore, with a given chemistry of the surface. And each time you change one of this stuff, for sure you have to change the kernel. So I'm going to now briefly show how it is done for the moment when you buy a gas porosimeter and that you want to analyze your measure. You choose your probe first, nitrogen, argon, CO2, depending on what you want to analyze, but also depending on this information you have there. So the probe and the condition. You measure your isotherm, which is also a topic in itself, and then you have to choose your kernel. And this is where the difficulty comes, because you have a specific material. It can be carbonaceous, it can be silica, it can be a morph, zeolite, etc. But you have, for the moment, let's say, a quite short list of possible kernels that are already available in the software. And so now what we maybe have to think to do is to generalize a bit these kernels to have more options, especially for the new absorbents that are done from recent years. So there have been latest developments, very interesting latest developments. I won't go into so many details for this one, but now what is proposed is to have a combination of several kernels, meaning you can change the shape of the pores, depending on if you are, for instance, in the microporous region, in the mesoporous one. And so you have a kind of combination of different kernels for a given probe. Just a combination of the two things we have seen. Then what has been done, and which is interesting, is that for the carbonaceous materials, the surface heterogeneity has been taken into account, because what has been observed is that considering smooth, homogeneous surface, like in smooth slit pores, led to artifacts into the pore size distribution. For instance, you have an artifact, you have a minimum in the pore size distribution, always around 1 nanometer, whatever the material finally you analyze, because it's a transition layer artifact you have when you go from one layer to two layers inside the pore. So what has been done is two modifications provided by two groups, the group of Neymark, who proposed what is called the quench solid DFT, in which finally now the surface of it's for carbonaceous material, essentially. So the surface of the first layer of carbon is still not homogeneous and smooth. You have here, you can see there, a decrease of density here of this first layer as a function in a small distance. The other, and it's what is done in the quantachrome porosimeter, what is used in quantachrome porosimeter. The second way of doing an equivalent, let's say, way, it's to work with DFT now in 2D dimension, what's called 2D and LDFT, where you can take into account both heterogeneity in surface energy, but also in geometry, meaning corrugation. And this was was proposed by Jagiello and co-workers and was introduced in micromeritics porosimeter. Here you've got an example of pore size distribution. You see the artifact at around 1 nanometer I talk about, and this is what you obtain when you take into account, for instance, corrugation or surface energy heterogeneity in the same material. So that's more or less the latest development that were done in this software. And if you apply that to carbonaceous material, we did some tests first I want to present the last thing. That was a last contribution also that was introduced, is the use of a combination of probes. So combination of kernel, but now by combining probes and using also of new probe. You have a recent article from Jagiello and co-workers that combine oxygen and hydrogen. Hydrogen in order to access to the smaller pore and to have a higher kinetics for the measurement. As with nitrogen, the measurement can be very long. And oxygen to have a lower quadrupole than for nitrogen or CO2. But finally, it's the same idea, but you combine two probes to have a complete picture of this material. So if you do so, let me show you just an example, because it can be seen quite simple, but finally you're going to see that it works not so bad. So I present you a work that was done in my group by one of my PhD students, Youssef, for which the thesis was on the coupling of DFT and poromechanics framework. So I'm just going to show you what we did about just one example on DFT. We were working on carbonaceous material, so it's the case here of an activated carbon. You measure the adsorption isotherm of argon at 87 Kelvin to have the obtained then the pore size distribution with the classical method I just presented. You have the pore size distribution, so here the cumulative volume and the pore size distribution. And what we were using in our side is a combination, of NLDFT and the soft formalism to model after adsorption at high pressure of methane and CO2, and also the swelling due to adsorption on this material. So first, if we just, for a check, if we use this NLDFT and soft combination to model again the adsorption isotherm, we could just analyze the influence of splitting this pore size in, let's say, 5 to 75 pore to see what is the influence of discretizing the pore size on the final result on global absorption. So we could finally represent the argon absorption, and for sure, as the number of pores you consider increase, so in green you can see the consideration of 75 pores, for sure you will have a smoother isotherm. It's the advantage, as I said in the beginning, to use DFT is the quickness of the calculation. The calculations are quite quick. If you use this simple picture for the activated carbon, finally, of this contribution of individual slit pores, and you recalculate with another DFT, so DFT combined with soft methane and CO2 absorption at higher pressure, I give you an example there. Finally, what you find is really not so bad. It's without any fitting of any parameter, so it's just prediction. And you see that finally, even these, let's say, simple pictures of, in that case, of the system, of this granular activated carbon, first, you are able to make a good prediction of, meaning the absorption of other fluid, methane, CO2, at high pressure and other temperature. And what you see also is that at this condition, finally, taking into account a very discretized pore size distribution, 75 pores or just 5 pores, finally the impact is not so important. And so finally, you're already able to do some interesting things with that. Anyway, it's because maybe you're dealing with quite similar fluids, you're dealing with static properties and not with dynamics properties. So for sure, there are also ways to progress. And so what was, let's say, analyzed as remaining challenge to do for the characterization of porous material, I've selected four for me that are important. First, what is the effect of connectivity, and could it be now taken into account? How to deal with new adsorbents, so MORPH, COF, zeolite. Now we have plenty of control synthesized porous adsorbent, and how to use gas porosimetry while we have just simple kernel at the moment. How to deal with flexible and switchable materials, which are more and more common. And last topic, could we use more complex probes, such as water, for instance? And so the last part of my talk is to say, okay, let us look at the recent DFT development to see what could they bring for that. I think we could summarize the last DFT development, in my opinion, like this. First of all, from several years now, several groups have worked on DFT that are based on molecular-based equation of states. Most of the time it's SAFT. And meaning that with that, we are now capable to study more complex fluids, associating fluid, for instance. An important also recent development in the application of DFT is the use of modern computing tools, especially used of fast Fourier transform, and the latest development by the team of Gross of GPU accelerating backward differentiation that really enables to treat 3D systems very quickly. And so to be able to study more now, this is for more complex fluid and now for more complex solids. And then also there are now people are used to, there are several examples of use of atomistic external potential, which is not traditionally done in DFT. So how can this development can be benefits, we can have benefits in adsorbent characterization? Let me just show you a very simple thing, to something done by Rafael, one of my PhD students, who is now finishing his PhD. Let's take a very simple configuration of two main pores connected by another one. As I told you at the beginning, you will totally neglect the connectivity in gas adsorption porosimetry. But if you simply compute the contribution of the main pore, here in red, the connecting pore, and you just make the sum of the contribution, you have this black curve. But if you compute directly, so for sure you are no more in 1D, you need a 3D calculation. But if you do so, or at least a 2D calculation, for sure you see that you have a different result, and that you cannot neglect the connectivity. So, and this will depend on the size of the pore, their diameter, the number of connections, and so on. So the idea is that could it, or at least should be included, now we are able to do so in 3D DFT. And so if I take into account the last results, there are recent papers showing that, especially for amorphous carbonaceous materials, that there have been some work on really novel procedures using visualization procedures, but also working with atomistic pore domain model, two different approaches to finally use database of 3D carbonaceous structure. And from that, and using these characterization tools, being able to use really more complex structure than just combination of slit pores for carbonaceous materials. And what has been done on the other part is showing, so I won't go into detail because it's a work of the group, so of your group, so you know it perfectly. If you apply, we are now able to apply 3D DFT in such a very complex system. And if you, in this paper, Lucas compare this result with the one of GCMC calculation and show that finally you are able to obtain equivalent results of adsorption, but with faster computation. And so I advise you to read this very nice paper from Nicolas Corrente and Professor Neymark that make a kind of point of what is done in this type of characterization, also for sweating material, because Nicolas worked also on sweating materials, and what could be done now if we use 3D DFT in this nanoporous carbonaceous material. Will it be really interesting to take this into account? So for sure the calculation are now possible. For sure it requires more time than the traditional calculation that takes just 1 second, let's say. The question for me is now, will it be important to do so for static, let's say static properties, static equilibrium adsorption? I think in some cases it won't be necessary, but in other cases, for doped carbon, for instance, it could be very interesting to do so. But another question is, what will be the impact on dynamic properties? And I think be able to characterize the nanoporous material like that now will help us to make very big improvement on understanding the dynamic properties of this fluid in such material. If I go now to the second topic, now the synthetic structure, let's say. The interesting thing now is that we are capable to deal with atomic structure. So meaning that we are capable to use an atomic structure. You've got a CIF file. you can introduce this in your DFT framework, and as you can do a 3D calculation, you can compute the adsorption in a given synthetic material. There have been several successful applications in MOF. So here also I take two examples. I think there are not so many papers, but there are a few now. A paper from Elvis. Here you have the example of methane adsorption in MOF5, and you can see that your DFT is really capable to even compute this high adsorption that gives this maximum of excess absorption of methane at pressure. So you have really results that are similar to molecular simulation and in very good agreement with experiments. And here is the work of Sand and co-workers on other MOF. So MOF5 also with methane and ethane and other MOF also. So you see now that it is possible to really compute the adsorption of a probe for a given MOF, and not a family of MOF, let's say, a given MOF for which you know the structure. Let me show you also a recent work. The publication is in progress, but it should be submitted soon to GFISCAM. It's a work of Rafael, who is one of my PhD students. He did the same stuff on zeolite, and the idea was to say, okay, can we begin with a CIF file of the zeolite, compute the adsorption in it, and compare that with the experimental result we perform in the lab. So just to picture about that, he has first work on ZSM5 as a not so complicated network. It's a kind of pole like that, crossing like that. And the interesting thing with ZSM5 is that by playing with the silica to aluminum ratio, you can have even no cation in the structure, no compensating cation. So it's the case when you have this silica to aluminum ratio. What Rafael has shown is that just by you can taking the CIF file, you take the force field from literature, and just by adjusting one parameter, the fluid to oxygen depth potential, by just changing it from 20%, you can reproduce the adsorption of methane and nitrogen at higher pressure and different temperature. You have three temperature from, as far as I remember, 300 Kelvin to 1400 Kelvin on this real zeolite. Then you decrease the silica to aluminum ratio, so now you have counterions, and you can just, by adjusting here also just the epsilon of the interaction between the ion and the fluid, obtain also very good results. And so the idea now is to say, okay, could it be used to investigate real structure, and especially it could help to see the difference between the theoretical structure that is synthesized, for which you know the unit self, and the real one you've got when you've got, for instance, 1 gram of sample, and be able to better investigate the defects, the binder content, and things like that on a real complex structure like that. Another example I want to talk about is flexible and switchable materials. Now, it's also work that has been done by Rafael in his thesis. You can use DFT in flexible material. The only thing you have to do is change the thermodynamic ensemble, because now you have no more fixed volume of the pore. So you have to deal with the osmotic ensemble. So what we did is that we have used finally what has been demonstrated by Kuder and co-workers with molecular simulation, is that you can separate the contribution and if you consider that the solid host energy is independent on the fluid itself, you can separate the osmotic potential into the ground thermodynamic potential computed in the ground canonical ensemble for the fluid, something you already do finally with DFT, the free energy of the solid, of the host itself, and this contribution from the stress upon the pore, which is somehow negligible when you're dealing with adsorption. So what Raphael did to show that is took, as was done earlier in molecular simulation, take the example of a bistable framework. So you have here your host contribution, which is defined as an asymmetric double well potential. We have chosen here a preferential state on the large pore configuration, but you can do as you want. It's a kind of structure that mimic MIL53. And so what you have, the interesting parameter is this one, the difference in energy between the narrow pore configuration and the large pore one. You can, so if you do so, you can compute adsorption isotherm and the ground potential of the fluid as a function of the opening angles. So you go in green, it's the narrow pore configuration, and as you go to purple is the large pore configuration. And you see for sure the change in the adsorption is isotherm, but what is interesting is that you see the change in the ground potential, because you see that for the lowest pressure, finally, the ground potential is minimum for the narrow pore configuration, but at some point you have a change. And due to the adsorption inside the cavity, finally now the larger pore begin to have the smallest ground potential. And so finally, if you compute the osmotic potential as a function of the pressure and the opening angle, what you can see as in red are the minima of this surface. You can see, for instance, in that configuration, in this choice of energy, that at the beginning, the narrow pore configuration is the most stable, and then at the highest pressure, the larger pore configuration becomes the most stable. And you can play with that. And for instance, you can play with the ratio between so this gap in free energy of the host, in the minima of the free energy of the host, and let me recall that the difference also you've got in the ground potential of the fluid. And if you play with this ratio, you will see that you will have the different configuration that you have in a breathing material. So as this host energy increase, the range where finally the ground potential, the impact, let's say, of the ground potential of the fluid prevails, decrease, becomes smaller and smaller until reaching just a point. And then it is not strong enough to compensate finally the host energy. And so here you have no more switch, you stay in the Laporte configuration. And then you can see like that you have different type of breathing going from large to narrow pore and then large pore again. Here, smallest range, here just one and then negative adsorption, and just here the large pore configuration. And so my idea that by being able to compute like that in osmotic ensemble, the path for the characterization of flexible materials is now open. And I will finish with the last topic because I think I'm a bit long. So for this last thing is we can use also more complex probe. Let's give me a last example. This is the PhD of Antoine, who just defended this year, who studied hydrogen bonding fluids such as water in his thesis. And what Antoine could do is derive a new functional of association that is suitable to work in any 3D geometry. And it's published in this paper. He came back to Vertem's original expression and could derive it, and finally the same assumption that are done in the bug version of that, in the Saft-VR equation, the bonded fraction, the not bonded fraction of associated molecule, and show that it can be expressed. So it's done by Antoine and Thomas Bernet, which is now in Imperial College. It can be expressed as a function here also of two weighted function, which is very interesting because by doing so, you can use the fast Fourier transform in the same way that you use for the FMT, sorry. And so it's a version which is finally quite similar to ISAR, but here in our version, we have an effective bonding region there of two associating molecules, while in ISAR you have just an exact bonding region. But the advantage is that there is no assumption restricted it to just one dimension calculation, so you can use it in any 3D geometry. So first, Antoine have shown that I've applied it, let's say, compared to molecular simulation to prove the efficiency of the functional, and could model associative molecule in, let's say, model cavity mimicking zeolites. So it's published in this paper. And then it could apply this formalism to obtain, for instance, the phase diagram of water confined in graphitic pore. And it's interesting because you can see what you are used to see, that the pore size finally, the displacement of the phase diagram and the condensation pressure with the pore size, which can be a good measure finally of the pore size. And what is interesting also is that it could show that you have a very big impact, it was expected, but a big impact of the especially temperature, so thermodynamic condition on the absorption of water. And you have a very big evolution of the mean density of water, depending both on pore size but also on temperature. And so the question now is this big influence of pore size, let's say temperature, but also for sure connectivity, surface chemistry, and so on, could be used to use water as a probe in gas porosimetry. For me, the question is not, I don't have the answer yet, let's say. It can be an advantage, but as it's complicated, it can be also a drawback. So let's say what it could bring also to adsorbent characterization. And so just let me conclude. I just rapidly go back to the four terms I've just said. Now, with recent development, we have 3D DFT that can be used to compute and to characterize more complex nanoporous material, especially nanoporous carbon. It is possible to compute also the absorption in MOF, COV, zeolite, and so meaning control synthesized porous structure. And it could be used also to make some progress in the investigation of the characterization of the real samples of these synthetic materials. With the DFT applied in osmotic ensemble, it could be possible to characterize flexible or switchable materials. And by the coupling of DFT with molecular-based equation of states, more complex probes could be used and could also open some paths, let's say, into gas porosimetry. And I will just end by acknowledge you for your attention, acknowledge my PhD student that done this work, and for sure the funding. I'm ready for if you have any questions.